Okay, in this video lesson, what we're going to do is talk about the relative strength of acids and bases, okay? And first thing we want to do with that is to kind of acknowledge the fact that what do we mean by strength, okay? Now, strength doesn't necessarily mean low pH. Strength does not necessarily mean high concentration, all right? Strength actually takes on a little bit different meaning when we talk about acids and bases. So the strength of an acid or base is relative to how many hydrogen ions for an acid or how many hydroxide ions for a base they generate. So if I put a mole's worth of acid into solution, what percentage of that acid generates hydrogen ions? Or if I put a mole's worth of base into solution, what percentage of that base generates hydroxide ions, okay? And the reason why we identify this is because when we have what we consider strong acids and bases, they're going to completely ionize in water, which means, for example, like our hydrochloric acid here, it's considered a strong acid. When hydrochloric acid dissolves into water, it almost 100%, for our purposes, we can say 100%, breaks apart into hydrogen ions and chlorine ions, okay? None of it forms in equilibrium staying HCl, okay? If you recall previous units where we talked about weak electrolytes and how when they dissolve in water, not all of those ions split apart. That's what we're talking about again here, but now we're just applying it to acid-base chemistry. So really, we're taking something that we already know and applying it to the acid-base chemistry side of stuff. Now, within our world, there are very few strong acids and strong bases. Okay, there's all kinds of acids and bases out there. But this table right here kind of summarizes what most people would consider the strongest acids and the strongest bases. And we give them the designate of strong because it actually, it doesn't just mean like, hey, they're tough. It just means that these are the ones that completely ionize, okay? So hydrochloric acid, hydrobromic acid, hydroiodic acid, chloric, nitric, and sulfuric. Now, one note for sulfuric acid, see little A here. Sulfuric acid it's actually diprotic, meaning it has two hydrogens to give. So for sulfuric acid, only the first hydrogen is the strong one, okay? Seems kind of weird. But when it ionizes, it actually ionizes in two steps. So it can give up one hydrogen ion very, very easily, okay? That is considered a strong acidic property for sulfuric acid. The second hydrogen ion, okay, does not always release. So to remove the second one would be considered a weak scenario, and we'll talk about that here in a second. Your bases are all of your alkali metals, lithium, sodium, potassium, rubidium, cesium, with hydroxide, okay? And most of your alkaline earth metals with hydroxides, okay? So it's pretty easy to identify your strong bases because they're going to have hydroxide on them for sure, and they come from the alkali metals and the alkaline earth metals for the most part, okay? There's a few exceptions, like beryllium hydroxide isn't considered strong, but I won't test you on those little exceptions, okay? It's good that you recognize these. So if we start talking about potassium hydroxide, you're like, oh, that's a strong base. I know it's going to completely ionize. Or if I talk about hydrochloric acid, you're like, oh, that's a strong acid. It was going to completely ionize, okay? In fact, if we take a look at these from the idea of their ionization, and we take a look at this table that we can add in here, notice how sulfuric acid, hydrochloric acid, nitric, the hydronium ion, all of these things when you start talking about equilibrium constants. Now this is Ka, so it's kind of like Keq, but it's a constant for acids, okay? Just as an example here. Notice how it doesn't even identify a number, it just says large. Because these numbers are so big, it is so product favored, it's so much greater than 1, which we know means product favored, that we can assume all of these are completely ionized in solution, okay? One thing to note is hydrofluoric acid right here, HF. Okay, so maybe on your notes over here, make a little note or something, put a little star saying not hydrofluoric acid for strong. Okay, and the reason why we note that is because hydroiodic, hydrobromic, hydrochloric, all of your halogen based acids are strong except for hydrofluoric acid. Okay, and the reason why, well, fluorine is so electronegative, is that fluorine likes to hold on to its hydrogen ions better. So it doesn't let those hydrogen ions separate in water as well. Water doesn't have enough strength to do its hydrogen bonding to pull that apart. Okay, so it actually kind of correlates back to things that we've talked about before, where fluorine being so reactive isn't going to give up that hydrogen ion and break that bond as well. So it's going to be considered a weak acid. Even though it's a strong bond, it's still a weak acid because it doesn't completely ionize in solution. Okay. Now, if we keep this idea rolling about our acids and bases, so what's it mean to be a weak acid or weak base? Okay, this means that they have a noticeable percentage that does not ionize in solution. So if you put a mole's worth of acid in solution, you're not going to get a mole's worth of hydrogen ions. Or a mole's worth of base, you're not going to get a whole mole's worth of hydroxide ions. So per unit, they're actually providing less hydrogen ions or less hydroxide ions, which means they're weaker because the properties of acids and bases come from the amount of hydrogen ions that get generated or how much they imbalance that water equilibrium we've been talking about. Okay? Now, when they do go into solution, they do form equilibriums. Okay? And we're going to go over to this animation by Fett. And this Fett animation, what I like about it is it does a really good job of visualizing that. Okay? So we'll bring this thing down in and take a look at it. And what we have here is we have considered a weak acid. So strength-wise, we've clicked over to weak. It's an acid. And right now the concentration is 0.01. So we're going to turn this thing up. And notice how if I change my concentration, as I put more of them in, you see more of them forming in the magnifying glass. If I take less out, there's less in there. Okay, so we're just going to put it like right around 0.1, someplace in there. There we go, 0.1 molar. Okay, so if we look inside at the microscopic view, we have the acid here. These are all in solution. Okay, these are all dissolved. Okay, so we put the water in there. There's all kinds of water behind this, but we're going to turn that off because the water or these molecules here just kind of get in the way of what we're trying to look at. So we're going to turn that off and ignore the water. So in solution, when this dissolves, this weak acid dissolves, some of them stay together, these grays, they stay together. Some split apart and make the conjugate base with that hydronium ion or those hydrogen ions again. But notice there's a significant amount that don't make these hydronium ions, all right? Now, if I were to strengthen this acid, okay, now you can't strengthen an acid, but for this simulation, I can say, well, what if this acid was stronger? Watch as I slide this thing over to the number of blue and red that show up on our screen. Okay? Hopefully by now you're noticing that we're getting a lot more blue and red. And for every one blue and red we put on, we're removing one of these grays. Okay? So the stronger our acid, the more this equilibrium is going to be product favored. Okay? We're going to make more hydronium ions, make more conjugate base, and use up this, which is preferred, right? For a strong acid, you don't want HA because the HA, the hydrogen is bound to the A, and it can't act as an acid in this case. It still acts as a typical ionic compound or even a molecular compound. This is where we get the acidic properties, is by making these. Okay, so the stronger we make this, you know, at some point we can almost, if we go all the way over, we can almost eliminate, not completely, because there's a few down here still, that in our system. Okay. Another way of looking at it, instead of looking at it through the molecular view, we can look at it through concentrations. Okay. So here's your concentrations. As I slide that to be stronger, notice how the concentration goes up while those concentrations go down on there. Okay. One other view, which is useful for us, if we make this thing really weak, if we go back to our concept of electrolytes, we see that the light bulb will light up because we do have ions in solution here because it is a weak electrolyte. Notice how it's not that strong. And then as I pull the slider over and make this stronger and stronger and stronger and stronger and stronger, okay, it's making these radial lines darker yellow and longer to represent more and more electricity being flowing. So the stronger the acid, the better electrolyte it'll be because we have more ions in solution. Again, that's a review thing. We've already talked about how electrolytes work in solution. Okay. Now we can do the same thing for bases. It doesn't change anything. It's the exact same scenario, except for we're producing a conjugate base and hydroxide ions instead. Okay. So the take home here is that if you have a weak acid or base, you're not going to get 100% ionization. So if you don't get 100% ionization, we form an equilibrium, okay? And if we form equilibriums, that means we probably want to have a way to quantify this, okay? And again, this is not new to us. We've already done this before. We've already done quantifying equilibriums because we've done KEQs. It's the exact same thing. So for us to quantify the strength of an acid or a base, we're looking at that K value again. Now, instead of saying KEQ, we say Ka because it is the equilibrium constant for acids. Or it could be Kb, the equilibrium constant for bases, okay? Same idea. Anything greater than 1 is considered strong, okay? Anything product favored, we consider a strong acid. Now, for acids, you don't really get things close to 1. So once you are above the 1 number, they go into the hundreds and thousands very fast, okay? Your general equilibrium expression is as follows. Everything is in solution, and then a certain percentage splits apart into ions, and a certain percentage stays together. So we can represent that by the hydrogen ions produced, the conjugate base that gets produced from this splitting, and the original unionized acid as your reactant, okay? One thing to note, if you have a polyprotic acid, each hydrogen in a polyprotic acid, okay, meaning diprotic or triprotic, has its own Ka value, okay? We mentioned it a little bit before, but so like, for example, we talked about sulfuric acid having 2 hydrogens in it. So that second hydrogen in sulfuric acid would have a different Ka than the first hydrogen. So for acid-base chemistry, you don't ever remove 2 hydrogens or 3 hydrogens at a time. It's 1 hydrogen at a time in terms of looking at it through that lens, okay? So is there a Kb? Sure. Yeah, if there's a Ka, there's a Ka. There's a Kb also. So constant for bases. Same idea. The only difference is that we need a little help from water to show this because we need to get hydroxide in our equilibrium, and not all bases have hydroxide in them to start. So if you take your base, including the water in that solution, you're going to get the conjugate acid now, which now it's gained a hydrogen with that base, and it's going to have that hydroxide, okay? So again, we see our Kb value is your conjugate acid, you have your hydroxide, and you have the original base that would be non-ionized in there, all right? So we can look at the relative strength of these things by just referencing their Kas and Kbs. So here's a table for us to take a look at. This one happens to just be a Ka table, but we can look and say, oh yeah, sulfuric acid, large, Ka. Formic acid, okay, it has a Ka of 1.8 times 10 to the negative 4. So it's considered a weak acid, okay? It's less than 1. It's going to only partially ionize in solution, okay? Looking down here, oh, look, there's water as an acid. It's 1 times 10 to the negative 14th. Oh, look, there's that 14 again that we've talked about before, okay? Which would make sense because its conjugate, the hydronium ion, has a Ka of 1. So these two together, if you multiply them, would equal the Kw. Side note. Here we have, let's find sulfuric acid, H2SO4. Notice how that one is large. If we go down here and find the hydrogen sulfate ion, now this is the second ionization of our H2SO4, we see that it has a Ka of 1.2 times 10 to the negative 2. Still relatively strong, but not considered a strong acid at this point, okay? So in terms of what it has over here. Carbonic acid, H2CO3, we see that, pretty weak. And then if you go down here, the hydrogen carbonate ion, the second ionization of that is even weaker, okay? So the second and third ionizations of an acid, if they're diprotic or triprotic, are always weaker as you do that, all right? We're not going to do much calculating with this beyond the stuff that we've done before in terms of KEQs, but for us, it's more a reference that, hey, if you want to know the strength of an acid or a base, you can reference a Ka table and say, oh, here we go, hydrofluoric acid, its Ka is times 10 to the negative 4, so it's going to be weaker than this acid, so it'll produce less hydrogen ions in solution, all right? That's what we're kind of looking at as we do our stuff. Now, why do we care? Okay, so all this stuff about strength of acids, so why do we care? What does that do for us in terms of the chemistry? Well, there's some conceptual things that we can take a look at because we're not diving deep into the math here. First is, the stronger the acid, the stronger the electrolyte, okay? So you're going to get more electrolytic behavior out of that, okay? The stronger the acid, the lower the pH at the same concentration, or the higher for a base, okay? So what I mean by that is, if I put 1/10 of a mole of hydrochloric acid into solution, or if I put 1/10 of a mole of a different acid solution, my pHs will not be the same. And I'm again going to bring that Fed app down in to show you what I mean by that. So we can get rid of this and get to our a pH meter now. If I go back to acids and I bring my concentration down, let's put it at 0.1. That'll work. Okay. And if I go to someplace in here for a weak acid and I drop my pH in, okay, so I'm getting a pH of 2.69, all right? Now notice, I'm not going to change my concentration, but if I make this a weaker acid, my pH goes up, okay? Because a weaker acid is going to have less hydrogen ions in solution. Remember, pH is directly related to those hydrogen ions in solution, okay? If I switch this over to a strong acid and make it a strong acid, a concentration of 0.1 has a pH of 1, okay? If I go to a concentration of 1, it has a pH of 0. Okay, a concentration of 0.01 or 10 times less concentrated has a pH of about 2. That should be exactly 2, actually, if it was reading right. Maybe it might have a fudge factor in there for fun. A concentration of 0.001 has a pH of 3. Okay, so you notice that as we take a look at these, these concentrations are directly related to those pHs. But if we go back to our weak acid again, take a look at the weak acid, now not changing this concentration, right? The concentration stays the same, but for a weaker acid, the pH would be higher. For a stronger acid, the pH would be lower. So what that means is we can actually use less acid to generate a lower pH for our strong acids, all right? Or what we're saying here is if I put a mole's worth of strong acid into solution or a mole's worth of weak acid into solution, the weak acid might drop my pH by a few points. The strong acid is going to drop it by way more, okay? Which means it's stronger. It can do more, that kind of stuff. All right? The stronger the acid, well, the more corrosive it is because the corrosive nature of acids comes from those hydrogen ions or those hydroxide ions. So again, the stronger it is, the more ions in solution, the more corrosive it becomes, okay? The stronger it is, the faster it reacts, okay? This goes back to our conversation on how concentration relates to the speed of a reaction. Well, more hydrogen ions, more concentration means faster reaction times, okay? So you have a higher concentration again, so it's going to react faster, okay? The more energy change we're going to see when it reacts, okay? Again, more ions are present, it's reacting faster, we're going to see a greater energy change. So everything gets more aggressive with stronger acids and strong bases, okay? They're the ones that are the most dangerous to us in terms of like corrosiveness or toxicity to people and organic tissue because of how corrosive they are, how fast they react, how big the energy change is, okay? Now, they're also better at neutralizing. We haven't talked about neutralizing yet, but neutralizing is the counteraction of a base to an acid. So an acid can actually neutralize a base. Now, one thing to note, they're not safer, okay? They're better at it, but not safer. And the reason why is because we have way more heat generated in that neutralization process because it happens faster, there's more energy change there. So even though the process is better, meaning it results quicker and easier, it also generates lots of heat energy. So that can be actually pretty dangerous for us, okay? And then last and most important, it's way more dangerous for us to handle, okay? So if you're working for a company and you're trying to decide on the chemicals you want to use, and you have strong acids versus weak acids, and their relative strength will play a role in what kind of personal protective equipment that your employees will have to be wearing, okay? I got a buddy who does this out in California, and he's walked into companies and said, well, you're using this acid, you're using this strength of acid, your employees have to have face masks, gloves, full suits, that kind of stuff. But then he'll say, but if you switch to this acid, it can still accomplish the same thing you wanted to chemically, and now all they need to wear is safety goggles and gloves. So it also creates a safer work environment. So part of his job is actually to take a look at these kind of things and say, hey, here's a way that you can accomplish what you still want, and it's better for your employees, it's safer for them and actually more comfortable for them. So that knowledge is something that he actually uses in his job every day as an environmental consultant out in California. Kind of cool. All right. All right. Now, we're going to end the video here because the next thing happens is we're going to talk more about that neutralization thing. Thank you.